Welcome to Spring LIB.
For this problem, we have been given a series of eight lists of integers. And for each list, we need to see if we can figure out a formula or rule that generates the terms of this sequence. Using that rule, we need to find the next three terms. So in each of these cases, we're going to be looking at how we get from one number to the next. Is there a common difference? Is there a common ratio? Is there a pattern to the differences? If we're alternating back and forth between numbers, what seems to be the rule governing when we alternate? So those are some of the things that we'll be thinking through for each of these problems. So let's start with the first one. 3, 6, 11, 18, 27. So we are increasing. Every term here is bigger than the one before. Let's take a look at our gaps. We have a gap here of 3, 5, 7, 9. Okay, while it is not a consistent gap, I definitely see a pattern here. These are the odd integers. And let's see if we'll just see if it keeps going. We have 11, 13, 15, 17. It definitely continues. So my next gap would be 21, which gives me 123. Then I should have a gap of 23, which is 146, and a gap of 25, which gives me 171. Okay, how about our second series? Again, let's examine the gap. How big is that gap between my numbers? In this case, it looks like a consistent gap. It looks like I'm adding 4 in between each set of numbers. So that's going to give me 47, 51, and 55. Okay, next pattern. I am increasing, but these numbers are definitely unique. They all are just 0 and 1s. And if you look at them, I start out with 1 digit, then I end up with 2. Then I have a set of 3, then I have a set of 4. These are the binary numbers in order. I'm counting up by 1 in binary for each of these. If you haven't really seen binary or done much with it, you can look at chapter 4.2 and get a little bit of information about binary numbers. But suffice to say, we count up, it counts just the same way we do with our normal base 10, except the only digits we have are 0 and 1. So in this case, I'm at 1011, which means I have to tick up to 1100. I add 1 and I add 1. So those are the next 3 binary numbers in this sequence. Okay, next numbers. I'm increasing, but I'm not going to be looking at the gap here because I have the same number repeating multiple times. So what we really need to know is what governs when we move and which numbers are included in this sequence. Well, looking at the numbers, we have 1, 2, 3, and 5. These are Fibonacci numbers. The next Fibonacci number would be 8, so I'd expect the next time we transition to be going to an 8. How many of each of these are there? Well, I have 1, 3, 5, 7. It looks like I'm going to have 9 8s coming up next. So my next 3 digits should all be 8. Okay, next set. Anytime you have huge changes in numbers where I'm getting progressively very, very, very much bigger, something good to look at are exponents or powers or factorials. Either one of those, especially if they get enormous, factorials is a great place to look because factorial numbers get very large very fast. So let's see what we're actually doing here. For this one, they're not getting so big so fast that I would expect it to be a factorial, but it could be a power. I could also just be multiplying by something. So let's see what we have. Going from 0 to 2 cannot be a strict multiplication because 0 times anything would stay 0. Since I'm starting at 0, I know at some point I have to be most likely adding something. So maybe think about adding a plus 2 because that's the simplest way to get from 0 to 2. Simplest isn't always right, but it's a good place to start. What about going from 2 to 8? Well, I could say that that's, if I want to have that plus 2, I could say that's 2 times 3 and then a plus 2. Or I could say that's 2 plus 2 times 2. Either way, I can include that plus 2 and come up a little. So let's see. Let's take a look. It's the first one I wrote down. So let's take a look. So if I say 2 times 3 plus 2. What about 8? 8 times 3 would be 24 plus 2 is 26. Well, that kind of worked. How about 26 times 3 plus 2? Well, that's 80. 80 times 3 plus 2 is 242. So it looks like I'm going to take whatever number I have times 3 plus 2. I could have checked this one out first. This one would not have worked. In this case, I'll just kind of show. If I had said it was 8 plus 2, that would have been 10 times 2 was 20. So that one, if I had chosen that one to try first, it would not have worked. We just kind of got lucky that it was the first one I tried. Okay, so next 3 terms. If I take 19,682 times 3 plus 2, I'm going to get 59,048. Times 3 plus 2 gives me 177,146. And doing it one more time gives me 531,440. Okay, the biggest help for this one was that very first gap, knowing that it wasn't just going to be a multiplication. I had to be doing something to get off of that 0. So that gave me the clue for the plus 2. Again, there's other ways to do it, but always start simple if you can. Okay, this next one, these are very large numbers. So I'm going to either be multiplying by a lot of numbers. I could have a factorial in here somewhere. Now, just as a reminder, let's just write out some of these factorials. Sorry, I miscopied that. It's not 4, it's 2. 3 factorial is 6. 24. Okay, so those are the first few. These numbers don't really seem to mesh with this because they're actually getting, at least these first few are getting bigger even a little bit faster than this. So how do I get from one number to the next? I'm going to just put this aside here because we might need it. It's always good to know those. This is a good spot to check. Didn't work this time. And that's okay on these. A lot of this is a little bit of a trial and error. There's not a hard and fast way to find it. You just have to try things out, see what's possible, try it. It might work. It might not. Okay. Last time around, what I tried worked first time. Here, I thought it might be factorials. I don't really see a way to get from those numbers in green to the sequence we have. So let's see another way to look at this. We have 1, 3. Well, 15 is 3 times 5. 105 is 3 times 5 times 7. Ooh, this looks promising. 945, 3 times 5 times 7 times 9. Okay, so it's kind of factorial in that we keep multiplying by numbers, but it's not every number. It's the odd numbers. So you can think of this as like odd number factorial. 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7, and so on. So this next one, I'm going to be multiplying the previous number by 11, by 13, by 15, by 17. This would be a good one to put in your calculator just to make sure that you really do have the rule. If it works, you do, and it does. So for down here, I'm going to be taking that prior one, multiplying it by 19, by 21, and by 23. So when I do this, when I multiply that last one that they gave us by 19, I end up with 654,729,075. And then these numbers get too big for my calculator. So it's 1.37 times 10 to the 10th, approximately. And approximately 3.16 times 10 to the 11th. Okay, so very big numbers. Again, you see these huge numbers. Factorial is a good place to go. While this wasn't strictly factorial, it was the right idea. Okay, next one. We're back to a sequence of ones and zeros, so we can leave the calculator alone for this one. What's the rule governing how many and when we switch? Well, I have 1 1, 2 zeros, 3 ones, 4 zeros. It looks like each time we switch, we add 1. So our next thing should be 6 zeros. So those would be the first 3 of those next 6 in the pattern. Okay, last one. Okay, talk about big numbers. This is pretty large. How am I going from one to the next? Well, these first few hopefully give you some ideas because these are all perfect squares. These are powers of 2. So we have 2, we have 2 squared, we have 4 squared, we have 16 squared. It looks like we are squaring each successive number. So try putting into your calculator and square and see if you get this large number here. Was that 4,294,000,000? You should get that number on your calculator. So it looks like for every term, we are squaring the prior. Now for this one, right off the bat, none of these numbers fit on my calculator. So it's approximately 1.8 times 10 to the 19th, 3.4 times 10 to the 38th, and 1.16 times 10 to the 77th. Okay, so these are some simple rules or formulas for each of these sequences, plus the next 3 terms.